Tonight, we're going to take a journey to the most dangerous place any human being has ever chosen to call home. Not a jungle, not an ocean floor, not the frozen peaks of the highest mountains on Earth. We're going to walk slowly and deliberately across the surface of Mars, a world that sits roughly 140 million miles away from everything you have ever known. A world so hostile, so silent, so utterly indifferent to human life, that every single second spent there will be a negotiation between ambition and survival. And here is the thing most people don't realize. The humans who make it there first won't just be explorers, they will be the last of their kind. There is a truth buried beneath the celebrations, beneath the rocket launches and the flag plantings and the tearful transmissions back to Earth, that almost never gets mentioned. The moment a human being sets foot on Martian soil, a clock begins. Not a countdown to rescue or return, a countdown to transformation. Because Mars does not simply challenge the human body, it rewrites it, quietly, patiently, without mercy. The gravity is 38% of what you feel right now. The atmosphere is less than 1% as thick as the air filling your lungs in this moment. And above that paper-thin sky, a constant invisible rain of cosmic radiation falls without pause, day after night after day, reaching the surface with nothing standing in its way. The first humans on Mars will begin to disappear the moment they arrive. Not all at once, slowly, in ways that are, in the truest sense of the word, terrifying. By the end of tonight, you're going to understand exactly why the bravest people our civilization has ever produced will step onto another world, and in doing so, step away from our world forever. You're going to understand what happens to a human body stripped of the gravity it evolved inside over 4 billion years. You're going to understand what radiation does to DNA across decades of exposure, what isolation does to a mind cut off from everything familiar, and what happens to the children born under a salmon-coloured sky who will never once feel the weight of Earth beneath their feet. You're going to understand how two branches of the same species could, across just a handful of generations, grow so different from one another that the word human may one day need two definitions. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Imagine standing in front of a mirror. Not the kind hanging in your bathroom, not the kind you glance into before leaving the house in the morning. Imagine a mirror so large it stretches from the floor to the ceiling of the sky, and when you press your hand against it, the glass is cold. Brutally cold. And on the other side, barely visible through the faint reflection of your own face, is a world unlike anything your eyes have ever adjusted to. Red, rust-coloured, vast and absolutely still. That is Mars. And that mirror, the one you're pressing your hand against right now, only opens one way. We have been looking at Mars for a very long time. Longer than telescopes existed. Longer than the written word. Ancient Babylonian astronomers tracked its movements across the night sky more than 3,000 years ago, noting its reddish glow and its peculiar habit of occasionally appearing to move backward against the stars. The Egyptians called it Her-Desha, the Red One. The Romans named it after their god of war, not because they knew anything about its surface, but because its colour reminded them of blood. For most of human history, Mars was simply a light in the sky, a mystery with a heartbeat, something that moved, which meant to ancient minds something that lived. We have been projecting our hopes and our fears onto that red point of light for millennia, and we have never quite been able to stop. And then, one by one, we began to send machines. Mariner 4 flew past Mars in 1965 and sent back 22 grainy photographs that shattered the dream of canals and civilizations. The surface was cratered, dead, and airless. Viking 1 landed in 1976 and scooped up soil looking for signs of life, and found, depending on who you ask, either nothing at all or results so ambiguous that scientists are still arguing about them today. Pathfinder, Spirit, Opportunity, Curiosity, Perseverance. Decade after decade, we sent our proxies ahead of us, rolling slowly across the ancient rust, drilling into rocks that had not been touched since before complex life existed on Earth. We were learning, we were preparing, and somewhere along the way, the question quietly shifted from whether humans could reach Mars to when. Here is the thing most people don't realize about that shift. The moment the question became when instead of if, an entirely different set of questions should have risen alongside it. Not just the engineering questions, the fuel and the rockets and the life support systems. Not just the logistics of keeping a small group of human beings alive on a barren world for years at a time. Something deeper. Something that sits beneath all the mathematics of orbital mechanics and habitat design, and asks very quietly what actually happens to a person who goes there and stays. What happens to their body? What happens to their mind? What happens to their children? What happens, across enough generations, to the very thing that makes them human? These are the questions that tend to get left out of the press releases, and they are, in the most genuine sense of the word, terrifying. Let me be clear about something before we go any further. The people who will one day stand on the surface of Mars will be extraordinary. They will be the most carefully selected, most rigorously trained, most psychologically resilient human beings our civilization has ever produced. They will volunteer for a mission knowing every risk that can be quantified and accepting every risk that cannot. They will look up at a pale pink sky and feel something that most of us will never feel, a particular species of awe that can only come from standing somewhere no member of your kind has ever stood before. They will be celebrated. They will deserve to be celebrated. And they will also, from the very first moment of their arrival, begin to change in ways that cannot be undone. The word disappear might sound dramatic. It might sound like the language of fear rather than the language of science. But I want you to sit with it for a moment because it is actually the most precise word available for what we are describing tonight. To disappear does not necessarily mean to cease to exist. It means to pass from one state into another, to become something that was not there before, while the original thing is no longer visible. A caterpillar disappears inside its chrysalis. It does not die, it transforms. But it will never be a caterpillar again. The first humans on Mars will enter a world that will do to them, over months and years and decades and generations, what the chrysalis does to the caterpillar. And there is no cocoon in the universe that opens in reverse. Consider the numbers for just a moment, because the numbers are where the reality of this lies. Mars has a gravitational pull that is 38% of Earth's. That means if you weigh 170 pounds here on Earth, you would weigh roughly 65 pounds on Mars. That sounds pleasant, perhaps even appealing, like walking through life permanently lighter. But your body was not designed for light. Your skeleton was built under pressure. Your cardiovascular system was engineered by 4 billion years of evolution to pump blood against a specific gravitational load. Your muscles were shaped by a world that pulled at them every single second of every single day. Remove that pull, even partially, and the body begins to quietly dismantle the infrastructure it no longer needs. Bones thin, muscles waste. The heart, freed from its gravitational burden, slowly shrinks. And every day that passes on Mars is a day the body drifts a little further from the blueprint of Earth, and that is just the gravity. That is just one layer of what Mars is doing to a human being standing on its surface. Above them, the sky offers almost no protection from the radiation pouring in from the sun and from deep space. On Earth, our magnetic field and our thick atmosphere absorb and deflect most of that energy before it ever reaches us. On Mars, the magnetic field essentially vanished billions of years ago, and the atmosphere is less than 1% as dense as ours. Radiation hits the Martian surface continuously. It accumulates in tissue, it breaks chemical bonds in DNA. Over months, it reaches doses that no occupational safety standard on Earth would permit. Over years, it becomes something else entirely. Over a lifetime spent on Mars, it is one of several forces quietly and methodically rewriting the people who chose to stay. And yet, despite all of this, humans will go. I believe that with a certainty that feels almost physical, because this is what our species does. We look at the most inhospitable places imaginable, and we ask, quietly and then louder, what it would feel like to be there. We crossed oceans in boats made of wood. We descended into the deepest trenches of the sea. We stood on the summit of Everest and looked down at the clouds, and then came back and told other people what it looked like, so that they would want to go too. Mars is simply the next impossible place on a very long list of impossible places that turned out to be possible after all. and the first humans to land there will look back at us across 140 million miles of empty space and feel exactly what every explorer who ever preceded them felt, that the distance was worth it. Even if, as we'll come to understand tonight, they can never quite come all the way back. There is something unusual about the way human beings have always looked at Mars. Something that goes beyond scientific curiosity, beyond the natural impulse to catalogue and categorise the objects moving through the night sky. When ancient eyes tracked that reddish wandering light, there was an emotional quality to the attention, a pull, a feeling that is difficult to name precisely, but that you have probably felt yourself on a clear night, standing outside with the darkness all around you, looking up and sensing that the universe is not simply large, but somehow personal. Mars has always seemed, to an almost irrational degree, like it was waiting for us, like it was placed just close enough to notice and just far enough to want. The Babylonians, who were among the most meticulous skywatchers the ancient world produced, called Mars Nergal, after their god of death and pestilence. They tracked its movements across the sky with remarkable precision, noting the periods when it seemed to reverse its course, a phenomenon we now understand as retrograde motion, the result of Earth and Mars orbiting the Sun at different speeds. To them, these reversals were omens, moments when the universe was sending a message, if only you were disciplined enough to read it. What is remarkable is not that they were wrong about the message. What is remarkable is that they were paying close enough attention to notice the pattern at all. They were watching Mars the way you watch something you do not fully understand but cannot bring yourself to look away from. Move forward across the centuries and the obsession only deepens. In the late 1800s, an American astronomer named Percival Lowell built an observatory in Flagstaff, Arizona, specifically to study Mars. He had become convinced, based on earlier observations by the Italian astronomer Giovanni Schiaparelli, that the surface of Mars was crisscrossed by long straight lines. Schiaparelli had called them canali, an Italian word meaning channels or grooves. Lowell translated this as canals, and from that single word an entire civilization bloomed in his imagination. He spent years at his telescope, mapping what he believed were vast irrigation networks built by an intelligent Martian race, a dying people on a drying world, engineering their survival with desperate ingenuity. He published books, he gave lectures, he made Mars feel not just possible but inhabited, and the world listened with a hunger that tells you everything about how badly humanity has always wanted a neighbour. Lowell was wrong, of course, completely and almost poignantly wrong. The lines he saw were artifacts of the limits of his telescope and the limits of human perception, the brain's tendency to connect faint, ambiguous shapes into meaningful patterns. There were no canals, there were no engineers, there was no dying civilization reaching across the void for help. But here is the thing worth sitting with, the desire that drove Lowell to that telescope, the longing that made him see order and intention in the rust-coloured blur of a distant world. That desire did not go away when the spacecraft arrived and showed us craters and deserts and silence. It transformed. It became something quieter and more serious. It became a plan. Carl Sagan, who understood the emotional weight of the cosmos better than perhaps anyone of his generation, wrote about Mars with a tenderness that is almost aching to read. He described it as a world that beckons, and he meant that word literally, not poetically. He believed that the question of a life on Mars, past or present, was one of the most important questions our species could ask, because the answer would tell us something fundamental about whether life is a rare accident or a common feature of the universe. He also believed, and argued passionately, that humans should go there in person, not just robots, not just cameras and spectrometers and soil scoops. People, with their eyes and their hands and their irreplaceable ability to recognize something unexpected when they see it. Sagan understood that Mars was not just a scientific destination. It was a mirror, and what we would find there would tell us as much about ourselves as about the planet. The dream accelerated through the second half of the 20th century in ways that felt, for a brief period, almost inevitable. The Apollo program proved that humans could leave this world and return. The Viking landers proved that we could put sophisticated machines on the Martian surface and keep them running. By the 1980s and 90s, serious mission architects were drawing up plans, calculating trajectories, estimating costs, imagining the moment when a human boot would press into Martian soil and leave a print that would remain undisturbed for thousands of years, because there is no rain on Mars. No wind strong enough to erase a careful footstep. Nothing to undo the mark of a visitor in the ancient dust. The footprint would simply stay there, perfectly preserved, long after the person who made it was gone. And then the dream ran into the oldest obstacle dreams encounter: the distance between imagination and logistics. Mars is not the Moon. The Moon is roughly 239,000 miles away. On Apollo 11, it took 3 days to get there. Mars, at its closest approach to Earth, is still about 34 million miles away. At average distances during a practical launch window, the journey takes somewhere between 6 and 9 months each way. That is 6 to 9 months inside a spacecraft smaller than a modest apartment, exposed to radiation, breathing recycled air, eating processed food, watching the Earth shrink behind you until it disappears into the background noise of stars. And when you arrive, the planet offers you nothing. No breathable air, no drinkable water on the surface, no warmth, no shelter that wasn't carried from home. The dream had to grow up, and growing up meant confronting everything that the dream, in its most romantic form, had preferred not to think about too carefully. But here is what I find most remarkable about this story, the part that moves me every time I return to it. The dream did not die when it grew up. That is not how this particular dream works. Every obstacle that emerged, every calculation that revealed a new layer of difficulty, seemed only to intensify the commitment of the people working toward it. Engineers designing radiation shielding, psychologists studying isolation and confinement, biologists asking what 6 months in space does to the human spine, the human eye, the human immune system, nutritionists calculating how to grow food in Martian soil, geneticists beginning, quietly and carefully, to ask what it would mean to modify the human body itself for life on another world. The dream did not refuse to die because people were naive about the obstacles. It refused to die because the obstacles somehow made it feel more worth doing. That is the contradiction at the heart of everything we are going to explore tonight. The same qualities that make humans want to go to Mars, the stubbornness, the hunger for the impossible, the willingness to accept costs that rational calculation would reject, are the qualities that will send the first crews into a transformation they cannot reverse. They will go knowing the risks, or at least knowing the risks that can currently be measured, and they will go anyway, because that is what this dream, the one that refused to die through Babylonian omens and Lowell's imaginary canals and Vikings' ambiguous soil samples and every budget cut and political shift, and failed mission along the way, has always demanded of the people willing to carry it forward. Everything, and they will give it. Picture the morning of the launch, not the press conferences and the countdown clocks and the crowds gathered miles away behind safety barriers. Picture the quiet part, the hour before any of that, when the crew is already suited and sealed and the technicians have stepped back, and there is nothing left to do but wait. Picture the faces inside those helmets. Not afraid exactly, because fear at that point has been processed and metabolized through years of training until it becomes something else. Something closer to a very deep and very still form of attention. They know what is coming. They have rehearsed every failure mode, every emergency protocol, every decision tree that branches off the moment something goes wrong at altitude. What they cannot rehearse is the feeling of the ground falling away beneath them for the last time. That part you can only do once. The journey from Earth to Mars is not like any journey human beings have taken before. It is not like crossing an ocean, where the water is hostile but the destination is another part of the same world, breathing the same air, pulled by the same gravity, warmed by the same sun at roughly the same distance. It is not like the journey to the Moon, which lasted 3 days and kept Earth so large and close in the window that the astronauts could cover it with a thumb. The journey to Mars, depending on the orbital alignment at launch and the trajectory chosen by the mission planners, takes somewhere between 6 and 9 months. 6 to 9 months in a vehicle with the interior volume of a small apartment. 6 to 9 months during which the Earth will shrink from a world to a country to a city to a dot to, eventually just another point of light among billions. And then it will become something harder to describe. Home, seen from a distance so great that the word home starts to feel like a concept rather than a place. The spacecraft the crew travels in will be an extraordinary feat of engineering. Every cubic meter of interior space will have been designed and redesigned dozens of times, optimized for weight and utility, and the psychological needs of people who will spend half a year inside it. There will be sleeping quarters barely wide enough to turn around in, exercise equipment the crew must use for at least 2 hours every day simply to slow the rate at which their bodies begin to deteriorate, a small common area where they will eat and talk and try to maintain some version of normal human social rhythm, and workstations where they will conduct experiments and monitor the spacecraft systems and, in whatever time remains, try to find ways to make the hours pass. Outside the reinforced walls, the temperature of space will be hovering around minus 270 degrees Celsius. The nearest human being will be measured in millions of miles, and the silence outside will be total and permanent and completely unlike any silence you have ever experienced on Earth, because on Earth, silence still has texture. The silence of space has nothing. One of the things that surprises people when they first learn about long-duration spaceflight is how quickly the small things become the large things. Astronauts returning from extended stays on the International Space Station, which is only about 250 miles above the Earth's surface, consistently report that the psychological challenges are not the dramatic ones, not the equipment failures or the medical emergencies, but the accumulative weight of the mundane. The same faces every day, the same recycled air with its slightly metallic aftertaste, the same sounds from the ventilation system that you stop noticing consciously, but that your brain never fully tunes out, the same view from the same window showing the same darkness, with different stars in the same arrangements, night after night after night. On a Mars mission, this will last not weeks but the better part of a year, and the Earth will not be visible in the window offering the psychological anchor that ISS astronauts can still rely on. The crew will be, in a way that no human beings have ever been before, genuinely alone. The communication delay alone changes everything in ways that are difficult to fully appreciate until you sit with them. Right now, if something is wrong, you can call someone. You can speak and be heard and receive an answer within seconds. That is so fundamental to how human beings manage stress and uncertainty that we barely think of it as a technology at all. It feels like a basic feature of reality. On a Mars mission, at average distances, a signal travelling at the speed of light takes roughly 20 minutes to reach Earth and another 20 minutes for a reply to return. 40 minutes for a single exchange. If a crew member is having a medical emergency, if a system failure is cascading, if someone is in psychological crisis and needs to hear a calm voice from home, that voice takes 40 minutes to arrive. Mission controllers have described this delay as one of the most psychologically significant aspects of the entire enterprise, and that is saying something given everything else on the list. And yet the transit itself, as demanding as it is, represents only the prologue to the real story. Because somewhere in the 5th or 6th month of the journey, something shifts in the crew's awareness. Earth has been gone from the window for a long time. Mars is still just a slightly brighter point of reddish light, growing incrementally larger with each passing week, but not yet large enough to feel real. They are between worlds in a way that is not metaphorical but literal. No planet has a meaningful gravitational claim on them. They belong in those weeks to the emptiness between, and it is in that emptiness, crew psychologists have theorized, that the full psychological weight of the mission begins to settle. The decision has been made. The launch was months ago. The surface of Mars is weeks away. There is nowhere else to go. Whatever is coming, and there is nothing to do but continue forward into it. The day of orbital insertion, when the spacecraft fires its engines to slow down and be captured by Martian gravity, will be one of the most tense moments of the mission. If the engine burn fails, or fires incorrectly, the spacecraft could skip off the top of the Martian atmosphere and continue into deep space, with no realistic possibility of recovery. If it fires too hard, the craft descends too steeply. The margins are extraordinarily tight, and the 40-minute communication delay means that by the time Earth knows something has gone wrong, the outcome has already been decided one way or another, without any possibility of intervention. The crew handles it alone. They always will. That is one of the defining conditions of this mission, and every mission that will follow it. The distance that makes Mars reachable also makes it unreachable in every way that matters when things go wrong. But let us say it goes right. Let us say the burn is perfect, the orbit is clean, and the descent vehicle separates and begins its fall through the thin Martian atmosphere. The heat shield glows, the parachutes deploy, the retro rockets fire, and then, after 6 months of travel and years of preparation and decades of our species dreaming about this exact moment, There is a soft and final impact, and the dust settles, and someone looks out a small thick window and sees the surface of another world for the first time with human eyes, red and still and ancient and vast, and beautiful in the particular way that places are beautiful when they are completely indifferent to your presence. The crew is on Mars, the journey is over, and something else, something none of them can fully see yet, has only just begun. The first thing you notice before anything else is the colour, not the red of fire or the red of autumn leaves or the red of anything warm and alive that you have seen before on Earth. This is an older red, a tired red, the red of iron that has been oxidizing for billions of years with nothing to interrupt it, no rain to wash it away, no life to consume it and transform it into something else. The sky above is not blue. It is a pale, dusty salmon, almost pink near the horizon where the finest particles of dust hang perpetually suspended in the thin air, catching the light of a sun that looks noticeably smaller here than it does from Earth, smaller and colder and farther away. You're 140 million miles from home, and the light itself is trying to tell you so. Step outside the habitat, sealed inside your pressure suit, and the silence is the second thing that reaches you. Not the silence of a quiet room or a remote forest, or even the silence of a night desert on Earth, all of which still carry texture and faint sound beneath them. This is a different category of silence. The Martian atmosphere is so thin, less than 1% as dense as Earth's at sea level, that sound barely travels through it at all. On Mars, you could stand 10 feet from a rocket engine firing at full thrust and hear almost nothing. The world around you, the endless Ross Plains, the distant crater rims, the rock fields scattered like broken teeth across the ancient ground, all of it exists in a quiet so complete, it feels less like an absence of sound, and more like a presence of something else. Something that has been here for 4 billion years, and has grown accustomed to the silence, and does not particularly need you to disturb it. The temperature will take longer to register, because your suit is working constantly to protect you from it. But the numbers are worth knowing, because they live at the edge of what is comprehensible. The average surface temperature on Mars is approximately minus 60 degrees Celsius. That is minus 76 degrees Fahrenheit. At the poles in winter, temperatures drop to minus 125 degrees Celsius. Even at the equator on a summer afternoon, the warmest Mars ever gets, the temperature might briefly touch 0 degrees Celsius, before plunging again after sunset with a speed and severity that has no equivalent in any inhabited place on Earth. Mars does not have warm days and cool nights. It has cold days and lethally cold nights, and the difference between the two can exceed 100 degrees Celsius within a single rotation of the planet. The thermal violence of Mars is constant, relentless, and entirely invisible to the naked eye. Look down at the ground beneath your boots, and you're looking at one of the most chemically hostile surfaces in the known solar system. Martian soil is not simply dirt in the way Earth soil is dirt. It is permeated with compounds called perchlorates, chlorine-based molecules that are toxic to human biology in even relatively small concentrations. On Earth, perchlorates occur naturally in some arid environments, like the Atacama Desert, but in concentrations far lower than what Mars presents across much of its surface. If you were to somehow bring Martian soil into contact with human tissue without protection, if you were to breathe the dust that Martian winds carry across thousands of miles of open terrain, the perchlorates would begin interfering with thyroid function almost immediately. This is not a minor inconvenience. This is the ground itself being actively poisonous to you. Mars is not simply indifferent to human life. In several specific and measurable ways, it is chemically hostile to it. And then there is the atmosphere. What little of it exists is approximately 95% carbon dioxide. There is almost no oxygen. There is no nitrogen in useful concentrations. The atmospheric pressure at the Martian surface is roughly the equivalent of what you would experience at an altitude of about 35 kilometers above Earth, which is 3 times higher than commercial aircraft fly and well above the threshold at which a human body, without pressurization, would lose consciousness within seconds and die within minutes. You cannot breathe on Mars. You cannot survive on Mars without a suit, without a habitat, without systems that carry your entire life support with you at every moment. Unlike Antarctica, unlike the deep ocean, unlike the summit of Everest, where the environment is extreme but still technically the same planet with the same basic atmospheric chemistry, Mars is not hostile in degree. It is hostile in kind. The difference is fundamental. Here is something that rarely gets mentioned in the celebration surrounding a potential Mars mission. The habitat the crew lives in will be, for months or years, their entire world. Not the vast rust plains outside, not the ancient volcanoes visible on the horizon, not the Val Marineris canyon system that stretches nearly the length of the continental United States and plunges 7 kilometers deep in places. Those things will be visible, sometimes, through thick reinforced windows and accessible, occasionally, during carefully planned and carefully limited excursions in full-pressure suits. But the lived experience of Mars, the place where the crew will eat and sleep and work and argue and laugh and cry and slowly transform, will be a pressurized volume roughly the size of a large recreational vehicle. That is not a complaint. That is engineering reality. Every gram of habitat material had to be launched from Earth's gravity well at extraordinary cost. Space inside that habitat is among the most expensive space in the history of human construction. The landscape beyond the habitat windows is simultaneously awe-inspiring and desolate, in a way that resists easy description. Mars is not a small world. Its surface area is almost exactly equal to the total land area of Earth, because Mars has no oceans. It has volcanic structures of a scale that makes Earth's largest mountains look modest. Olympus Mons, the largest volcano in the solar system, stands about 22 kilometers high and spans a base roughly the size of France. The canyon system of Valle Marineris would stretch from New York to Los Angeles if laid across the continental United States. Mars is enormous and varied and ancient in ways that geologists would spend centuries studying, and it is completely, utterly, profoundly dead. No bird song, no insect hum, no wind carrying the smell of rain on warm soil, no biological process of any kind that we have confirmed, anywhere, at any scale. The scale of Mars and the scale of its silence compound each other into something that is hard to sit with for long without feeling the weight of it. This is the world the first humans will wake up to on their second morning, and their third, and their 100th. This is the view that will greet them every day for as long as they are there, and while the scientific work will be consuming and meaningful, and historically significant beyond any reasonable measure, while the simple fact of being the first humans to stand on another planet will carry an emotional charge that never fully fades, the environment will also be doing something else at the same time, something quieter, something that happens at the cellular level, at the structural level of bone and muscle and eye and brain. Mars will be reading them, the way a river reads the stone it flows over, slowly and without hurry and with absolute patience, and it will begin from that very first day to leave its mark. Your body has a memory, not the kind stored in neurons and synapses, not the kind you can access by closing your eyes and thinking back to a specific afternoon in a specific place. This is a deeper memory, written into the architecture of every bone and every muscle and every system that keeps you alive without asking your permission. It is the memory of gravity. Specifically, it is the memory of one gravity, the pull of one particular planet, calibrated over 4 billion years of evolution to expect exactly 9.8 meters per second, squared, pressing down on every cell in your body, every moment of every day from the first second of your existence to the last. That number is not just a physical constant for your body. It is the environment your biology was designed to inhabit. Change it, and the body does not simply adapt. It begins quietly and efficiently to forget what it was built for. On Mars, the gravitational pull is 38% of Earth's. That means the constant downward pressure your skeleton has been experiencing since before you were born drops to less than half of what your body considers normal. For the first day or two, this might feel almost euphoric. You are lighter. Movement requires less effort. The ache in your lower back that you have carried for years dissolves. There is a temptation to interpret this lightness as a gift, as though Mars is offering you something. But your body is already beginning to respond in the only way evolution has equipped it to respond to a reduction in mechanical load. It starts dismantling the infrastructure it no longer believes it needs. This process begins not in weeks, but in days, and it does not wait for permission. Bone is not the static, inert material it looks like when you see it in a museum or an anatomy textbook. Bone is alive. It is constantly being broken down and rebuilt by two types of cells working in opposition. Osteoclasts, which dissolve old bone tissue, and osteoblasts, which lay down new bone in its place. On Earth, the mechanical stress of gravity and movement keeps these two processes in rough balance. Your bones remain dense because they are constantly being told, by the simple act of bearing your body's weight against Earth's pull, that density is necessary. Remove that signal or reduce it dramatically as Mars does, and the balance shifts. Osteoclasts continue their work, osteoblasts slow down, the bones begin to thin. Astronauts on the International Space Station, orbiting in near weightlessness, lose bone density at a rate of roughly 1 to 2% per month in the most load-bearing areas of the skeleton. On Mars, the rate would be slower due to the partial gravity, but it would not stop. It would simply proceed at a pace that is harder to notice, and therefore, in some ways, more insidious. The muscle loss runs parallel to the bone loss, and if anything, is even faster to begin. Skeletal muscle, the tissue that moves your body and holds your posture and gives you your physical strength, is metabolically expensive for the body to maintain. It requires significant energy and resources to keep in condition, and the body is ruthlessly practical about cutting costs when conditions change. On Earth, simply standing upright and walking through your day provides enough mechanical stimulus to maintain baseline muscle mass. On Mars, the reduced gravity means that even routine movement places less demand on the muscular system. The muscles of the legs, the lower back, the core, all the structures that evolved specifically to manage the business of living in Earth gravity, begin to shrink. Not dramatically at first, not in a way you would necessarily feel from the inside, but measurably, consistently, and in a direction that does not reverse itself without deliberate and sustained intervention. This is why mission planners mandate a minimum of 2 hours of vigorous exercise every single day for crew members on long-duration space flights. Not because the crew needs to stay fit in any conventional sense, because without it, the physical deterioration accelerates to a point where the ability to function is compromised. Astronauts returning from 6-month stays on the International Space Station frequently cannot walk unassisted when they first return to Earth's gravity. Some have to be carried from the capsule. Some take weeks or months to fully recover their pre-flight strength and coordination. Their bodies had adapted to the new environment with extraordinary efficiency, and readapting to the old one is a separate and demanding process. On Mars, the question of return and readaptation becomes far more complicated, for reasons we will return to in time. For now, the point is simply this. The body on Mars is not the same body that left Earth. It is changing. Every day. And exercise, as important as it is, can slow the change but not prevent it. The cardiovascular system responds to reduced gravity in its own particular way, and the changes here carry some of the most significant long-term implications. On Earth, your heart is engaged in a constant battle against gravity, pumping blood upward from the lower body against the resistance of the planet's pull. This demand keeps the heart strong, well exercised simply by the act of keeping you alive in a one-gravity environment. In reduced gravity, this effort decreases. The heart, like every other muscle in the body, responds to reduced demand by reducing its mass. Cardiac muscle atrophies. The heart itself becomes smaller and less powerful. Studies of astronauts have documented this effect even on relatively short missions, and the implications for people living on Mars for years at a time, or permanently, are something that space medicine researchers are only beginning to fully grapple with. A smaller, weaker heart is not simply a fitness concern. It is a fundamental change in the organ responsible for keeping everything else alive. There is something almost philosophical about the way the body responds to Mars, if you take a step back and look at it clearly. The human body is not malfunctioning when it loses bone density and muscle mass and cardiac volume on Mars. It is functioning exactly as it is supposed to function. It is reading the signals its environment is providing and optimizing accordingly. It is becoming a Mars body. Lighter bones for lighter gravity, smaller muscles for smaller loads, a heart calibrated for the world it actually lives in rather than the world it came from. From a purely biological standpoint, this is adaptation working as intended. The problem, the genuinely terrifying problem, is that the world the body is adapting to is not the world most of the species lives in. An adaptation, once it proceeds far enough, stops being a temporary adjustment and becomes a permanent condition. Researchers studying the long-term effects of reduced gravity have begun using a phrase that appears infrequently in official mission documents, but that captures the reality with uncomfortable precision: deconditioning cascade. It describes the way the physical changes do not occur in isolation, but interact and amplify each other. Bone loss increases fracture risk. Muscle loss reduces the ability to exercise effectively, which accelerates both bone loss and cardiac atrophy. Cardiovascular changes affect circulation, which affects the delivery of nutrients to bone and muscle. The systems are interconnected in ways that make the deterioration not linear but compounding. Each change makes the next change easier and faster to arrive. And underneath all of it, running silently and continuously, is the simple fact that every day on Mars is another day the body moves further from the specifications of Earth. Another day it forgets a little more of what it was built to be. Another day it becomes, in small but measurable and irreversible increments, something new. There is something above you right now that you cannot see, cannot feel, and almost never think about, and it is saving your life. It has been saving your life every second of every day since before you were born. It is the Earth's magnetic field, a vast invisible structure generated by the churning of molten iron in our planet's outer core, extending tens of thousands of kilometers into space in every direction, forming a protective bubble that deflects the constant stream of charged particles pouring out of the Sun and from the far reaches of the galaxy. Without it, the surface of the Earth would be exposed to a radiation environment that would have made the evolution of complex life essentially impossible. You have never once had to think about this shield. It has simply always been there, silent and total, and taken entirely for granted. On Mars, it is gone. Mars once had a magnetic field. The evidence is preserved in the ancient rocks of the Martian crust, bands of magnetized minerals laid down billions of years ago when the planet's interior was still active enough to generate a protective field similar to Earth's. But somewhere around 4 billion years ago, Mars's core cooled and solidified, and the dynamo that had been generating the field simply stopped. The field collapsed. The solar wind, the constant outflow of charged particles from the Sun, began stripping away the Martian atmosphere over millions of years, thinning it from something that may have once been thick enough to support liquid water on the surface to the near vacuum that exists today. The loss of the magnetic field did not happen overnight, but it was, in the long history of Mars, one of the most consequential events in the planet's evolution, from a potentially habitable world to the radiation-blasted desert it has become. And the first humans to live there will inherit all of it. The radiation environment on the Martian surface comes from 2 primary sources, and understanding them separately is important, because they threaten the human body in different ways on different timescales. The first is galactic cosmic rays, high-energy particles originating from supernovae and other violent events across the galaxy, travelling at close to the speed of light and carrying enough energy to penetrate significant amounts of shielding material. These are not like the radiation from an X-ray machine or even from the radioactive materials used in nuclear power. Galactic cosmic rays are among the most energetic particles in the known universe, and they pass through the thin Martian atmosphere and the walls of habitats and pressure suits and human tissue with a casualness that is genuinely difficult to comprehend. There is no practical way to fully shield against them with materials light enough to bring from Earth. They are simply part of the Martian environment, like the cold and the thin air, except that unlike the cold and the thin air, you cannot feel them arriving. The second source is the Sun itself. Solar particle events, intense bursts of radiation associated with solar flares, and coronal mass ejections can deliver acute radiation doses that are dangerous within hours. On Earth, the magnetic field deflects most of this. On the International Space Station, astronauts can shelter in more heavily shielded sections of the station during a major solar event and receive acceptable doses. On Mars, during a large solar particle event, a crew caught outside their habitat could receive a radiation dose equivalent to several years of normal background exposure in a matter of hours. The Martian atmosphere provides a small amount of additional shielding compared to being in open space, but it is nowhere near sufficient to make solar particle events safe for unprotected humans on the surface. The habitat walls and any additional shielding the mission brings will provide meaningful protection during these events, but the crew will need early warning systems and clear protocols, and there will always be the possibility that someone is too far from shelter when the storm arrives. Here is the thing most people do not realize about radiation damage in the human body. Most of it does not announce itself. It accumulates silently, at the molecular level, in the form of broken chemical bonds in DNA. Every cell in your body contains roughly 2 meters of DNA coiled into its nucleus, and that DNA is constantly being damaged and repaired by biological mechanisms that have been refined over billions of years of evolution on a radioactive, sunlit world. The repair systems are remarkably good, but they are not perfect. Some damage gets repaired incorrectly, creating mutations that persist in the cell's descendants. Some damage accumulates faster than it can be repaired, especially in cells that divide rapidly. Some mutations are harmless, some trigger cancer. Some affect cells in ways that are not immediately dangerous, but that alter the function of tissues and organs over time. The dose of radiation a Mars crew would receive over a year on the surface would not kill them quickly. It would increase their lifetime cancer risk significantly, and it would do other things as well, things that are currently less well understood and for that reason perhaps more concerning. Among the most troubling findings from recent research into space radiation is its effect on the brain. Studies conducted on astronauts returning from long-duration missions and on animal models exposed to simulated space radiation in laboratory settings have found evidence of neurological changes that go beyond what simple oxygen, deprivation, or stress could explain. Cosmic radiation appears to affect the central nervous system directly, damaging neurons and altering the behavior of glial cells, the support structures of the brain. In animal studies, exposure to the types of radiation found in space has produced measurable deficits in learning, memory, and decision-making. It has also been associated with increased anxiety-like behavior and changes in how the brain processes and responds to fear. These are not the kinds of effects that show up on a standard medical scan. They are subtle, cumulative, and exactly the kind of thing that would be almost impossible to distinguish from the psychological effects of isolation and stress in a real mission environment, which makes them particularly difficult to study and particularly difficult to prevent. The cumulative picture is one that space medicine researchers describe, in their more candid moments, as a series of overlapping and interacting risks with no clean solutions. You cannot simply build thicker walls, because the weight of adequate shielding against galactic cosmic rays would be prohibitive to launch. You cannot simply limit time on the surface, because the work of a Mars mission requires surface activity. You cannot simply medicate against radiation damage, because no pharmaceutical intervention currently available fully prevents the cellular and neurological effects of chronic radiation exposure at the levels Mars presents. What you can do is monitor carefully, design habitats with the best shielding currently practical, minimize unnecessary EVA time during known solar events, and accept, with clear eyes, that the radiation environment of Mars is one of the most significant medical challenges of human spaceflight, and that it will leave its mark on everyone who stays there long enough. And yet, when you consider what radiation actually is at its most fundamental level, there is something almost poetic buried inside the threat. Galactic cosmic rays are the debris of exploded stars. They are the remnants of supernovae that occurred thousands or millions of light years away, ancient stellar deaths whose energy has been travelling across the galaxy for eons, and will now, for the first time in the history of our species, pass through a human being standing on the surface of another world. The same particles that are slowly and silently accumulating damage in the DNA of the first Mars crew were created in the deaths of stars that burned out before our sun existed. There is a kind of dark intimacy to it. The universe reaching in, as it always has, through whatever shields we construct, to remind us that we are made of the same material as everything else, and that the same forces that built us are perfectly capable, given enough time and proximity, of taking us apart. We spend a great deal of time, when we talk about Mars, discussing the physical challenges, the radiation, the gravity, the cold, the toxic soil. These things are measurable and concrete, and they respond, at least partially, to engineering solutions. Build a better habitat, design a better suit, bring better medicine. The physical threats of Mars exist in a domain where human ingenuity has a long and impressive track record of finding answers. But there is another category of challenge waiting for the first Mars crew, one that is harder to quantify and harder to engineer around, one that operates not in bone or muscle or DNA, but in the space between a person and their own sense of who they are. The psychological environment of a Mars mission may ultimately prove to be as demanding as the physical one, and unlike radiation damage or bone loss, the effects on the mind do not show up on a scan. Psychologists who study long-duration spaceflight use a term that sounds almost gentle for what it describes: third-quarter phenomenon. It refers to a pattern observed repeatedly in isolated and confined environments, from Antarctic winter overstations to submarine deployments to simulated Mars missions conducted here on Earth. The pattern is this. In the third quarter of a long mission, roughly halfway between the midpoint and the end, psychological symptoms tend to peak. Irritability increases, motivation drops, sleep quality deteriorates. The sense of time stretching ahead without resolution becomes almost physically oppressive. Interpersonal conflicts that were manageable in the first half of the mission begin to calcify into genuine rifts. The third quarter is when people who were carefully selected and expertly trained start to discover the limits of their own resilience, not because something has gone wrong, but simply because a long time in a small space with the same people and no exit is, at a fundamental level, one of the most psychologically demanding experiences a human being can undergo. Now extend that timeline from months to years. Now remove the knowledge that the mission will end on a fixed date, and you will return to Earth and resume your former life. Now add the 40-minute communication delay that makes every exchange with family and friends and mission support a slow and unsatisfying echo rather than a conversation. Now add the awareness, present in the mind with varying degrees of intensity on different days, that you are farther from every other human being than any person in history has ever been. The nearest human life is not across an ocean or over a mountain range. It is 140 million miles away, across a void of space that takes light itself 11 minutes to cross in one direction. You're not simply remote. You are, in a way that has no historical precedent, genuinely and completely elsewhere. The communication delay deserves its own moment of attention, because its psychological effects are both profound and underappreciated. Human beings are social animals in a way that goes all the way down to our neurological architecture. We regulate our emotional states through contact with other people. We process stress by talking about it. We calibrate our sense of reality through the responses we receive from others. Even introverts, even people who feel most comfortable alone, are embedded in a network of social connection that they draw on continuously, often without noticing it. On a Mars mission, every attempt to reach into that network hits a 40-minute wall. You send a message to your partner and wait 40 minutes for any response. You call your mother on her birthday, and by the time she hears your voice, she has already moved on to a different part of her day. The conversational rhythm that underlies all human emotional connection becomes impossible to maintain. What replaces it is something flatter and slower and lonelier, even when the words being exchanged are warm and careful and full of love. Isolation research has shown, consistently and across a wide range of environments and populations, that prolonged social isolation does not simply make people unhappy. It alters how the brain functions. It affects memory consolidation, emotional regulation, impulse control, and the interpretation of social signals. People in long-term isolation become hypersensitive to perceived slights and interpersonal tensions, which is particularly problematic in the confined quarters of a spacecraft or habitat, where the same small group of people must collaborate closely on high-stakes tasks every single day. Studies of Antarctic winter overcrews who spend up to 14 months in extreme isolation with a fixed small group have documented a phenomenon called expeditioner's eye, where crew members who began the mission with normal social perceptions gradually develop distorted readings of other people's intentions and emotions, seeing hostility or indifference where none exists, or missing genuine distress signals in colleagues. A Mars crew would face all of this, and more, with no possibility of a rescue flight and no option to simply remove a troubled crew member from the environment. There is also the question of identity, which is quieter and slower moving than the more acute psychological challenges, but perhaps ultimately more profound. Our sense of who we are is not generated in isolation inside our own heads. It is constructed continuously in relationship with the world around us, with our roles, our relationships, our cultural contexts, our daily environments. The person you are is partly a product of the specific gravity of the world you stand on, the specific light of the star you orbit, the specific sounds and smells and textures of the place you call home. Remove all of that, replace it with the interior of a habitat on a dead world beneath an alien sky, and the self begins a slow renegotiation that is as disorienting as it is inevitable. Who are you when every reference point that helped define you is 140 million miles away? Who do you become when the world you inhabit bears no resemblance to the world that made you? Psychiatrists working with long-duration mission planning have begun studying a phenomenon they call overview effect extension, building on the well-documented experience of astronauts who report a profound shift in their sense of self and their relationship to Earth upon seeing the planet from space. For most astronauts, this shift is positive and transformative, a feeling of connection and perspective that many describe as one of the most meaningful experiences of their lives. But researchers are asking whether a longer and more permanent version of this disconnection, one that stretches across years rather than days, might produce something more complex and less clearly positive, a sense not of connected perspective, but of genuine detachment, a loosening of the emotional bonds that tie a person to the civilization they came from. Not homesickness exactly, but something harder to name, the beginning of belonging somewhere else. And yet, in the research and in the testimonies of people who have spent long periods in extreme isolation, something else consistently appears alongside the difficulties, something that is harder to measure but unmistakably present: resilience, adaptation. The discovery that the human mind, under the right conditions and with the right support, is capable of finding meaning and equilibrium in environments that seem, from the outside, almost unbearable. The people who go to Mars will not simply suffer the psychological environment of that mission, they will also be shaped by it into something their pre-mission selves could not have fully anticipated. They will develop new ways of experiencing time, new relationships with silence and solitude, new forms of intimacy forged under pressure with the small group of people who share their world. They will become, in ways both difficult and extraordinary, people that Mars made, and that making, as we will come to understand, does not stop when the mission ends. It continues into the generations that follow, carried forward by children who have never known any other world. There is a finding from human spaceflight research that, when I first encountered it, stopped me in a way that very few pieces of scientific information have. It is not the most dramatic discovery in the field. It does not involve the largest numbers or the most immediately life-threatening consequences, but something about its specificity, about the particular intimacy of what it describes, makes it land differently than statistics about bone density or radiation exposure. The finding is this: astronauts who spend extended time in space return to Earth with permanently altered eyes, not subtly altered, measurably, structurally, visibly altered, in ways that affect how well they can see for the rest of their lives. The eye, which we tend to think of as one of the most delicate and fixed structures in the human body, turns out to be surprisingly vulnerable to the conditions of space. And on Mars, the conditions that cause this transformation will be present every day for as long as anyone lives there. The mechanism begins with fluid. In the human body on Earth, gravity distributes fluids in a specific way. Blood and cerebrospinal fluid, the liquid that surrounds and cushions the brain and spinal cord, are pulled downward by gravity in a continuous and familiar pattern. Your cardiovascular system is calibrated to manage this distribution, pumping blood upward to the brain against gravity's pull, and relying on gravity itself to assist with drainage and return flow in the lower body. In reduced gravity, or in the near weightlessness of spaceflight, this distribution shifts. Fluids that gravity would normally draw downward migrate toward the upper body and the head. Astronauts on the International Space Station frequently report a sensation they describe as being like a permanent head cold, a persistent feeling of fullness and pressure in the sinuses and skull. This is not merely uncomfortable, it has structural consequences that compound over time. The increased fluid pressure in the skull pushes on the optic nerve, the cable of neural tissue that connects the eye to the brain, transmitting visual information from the retina inward for processing. Under sustained intracranial pressure, the optic nerve begins to change shape. The area where it enters the back of the eye, called the optic disc, can develop what ophthalmologists call papilledema, a swelling and flattening that distorts the geometry of the nerve. The eyeball itself, ordinarily a near-perfect sphere, can become slightly flattened at the back under sustained pressure. The retina can develop small folds. The lens, which adjusts its shape to focus light precisely on the retina, finds itself operating inside an eye that no longer has quite the geometry it was calibrated for. The result is a degradation of vision that is in many cases permanent. Several astronauts who have returned from long-duration missions on the International Space Station have reported that their eyesight never fully recovered. Some now wear glasses for the first time in their lives. Some have vision that fluctuates in ways they did not experience before their mission. The eye, it turns out, is a remarkably accurate record of what the body has been through. This condition has been given the name Spaceflight-Associated Neuro-Ocular Syndrome, often abbreviated as a clinical acronym that does a poor job of conveying just how strange and unsettling the phenomenon actually is. What it describes is essentially this: space is slowly and quietly reshaping the human eye, not in a gross or obvious way, not in a way that blinds anyone, at least not based on what we have observed so far, but in a persistent, cumulative, structural way that does not fully reverse when the person returns to Earth. And the critical question, the one that keeps researchers awake, is what happens when the exposure is not 6 months but 6 years, or 16, or a lifetime. The astronauts we have studied so far have all returned to Earth's gravity, which provides at least partial relief from the intracranial pressure driving the changes. A permanent Mars resident never gets that relief. The pressure, lower than in zero gravity but still elevated compared to Earth conditions, continues, day after day, year after year. Here is what makes this particular finding so philosophically arresting beyond the clinical implications. The eye is how we perceive the world. It is the primary instrument through which a human being takes in information about their environment, and in doing so constructs their experience of reality. To say that Mars will change the eyes of the people who live there is to say something that goes deeper than a medical observation. It is to say that Mars will literally change the way its inhabitants see, the light they perceive, the sharpness with which they resolve objects, the degree to which they can read fine detail. All of this will be different from what an Earth human experiences. And while the changes we are currently aware of are primarily in the mechanics of vision, rather than in its neural processing, the eye and the brain are not separable systems. Changes to one propagate into the other in ways that are still being mapped. There are additional visual challenges specific to the Martian environment that compound the biological ones. The light on Mars is dimmer than on Earth, because Mars is roughly 1.5 times farther from the Sun, receiving about 43% as much solar energy per square meter as Earth's surface. The quality of that light is also different. The dust suspended in the Martian atmosphere scatters and filters sunlight in ways that give the Martian day its characteristic pinkish quality, and that reduce the contrast and colour saturation of the visual environment compared to a clear Earth day. Human colour vision evolved under specific spectral conditions, calibrated over millions of years to the particular quality of light filtering through Earth's atmosphere. The visual system of someone living their entire life under Martian light would be operating in a persistently different spectral environment, and while the brain is remarkably adaptable in its colour processing, we do not yet know what years of this adaptation might mean for the neural architecture of vision. Astronauts and researchers who have spent extended periods in visually monotonous environments, whether in space, in Antarctic stations, or in sensory-restricted laboratory studies, consistently report changes in how they perceive visual detail and novelty upon return to a varied environment. Colours seem more vivid. Complexity seems almost overwhelming. The visual system, accustomed to the limited palette of its confined world, responds to the richness of the ordinary with something approaching sensory shock. A person who has spent years on Mars, surrounded by the particular rust reds and dusty pinks and dark starfields of that world, and who then somehow return to Earth, might find themselves physiologically and neurologically unprepared for the visual intensity of a forest or an ocean or a city street at midday. The eyes that returned would be eyes that Mars had made, calibrated to a different world, carrying in their changed geometry the record of a life lived elsewhere. And so we arrive, through this one specific and intimate detail, at something larger. The eye is a window, and not only in the poetic sense, it is a window into the biological history of the person behind it. When researchers examine the optic nerves and retinal structures of returned astronauts and find the subtle but unmistakable signatures of time spent in altered gravity, they are reading a record written not in words or memories but in tissue. Mars will write the same record more slowly and more deeply in the eyes of the people who make it their home. Long after they have stopped thinking consciously about the world they came from, long after the routines of Martian life have become simply life, the record will still be there, pressed into the geometry of the eye, carried in the architecture of the optic nerve, a quiet and permanent annotation in the body's long account of everywhere it has ever been. Every hostile environment human beings have ever chosen to inhabit has offered something in return. The Arctic offers seals and fish and trade routes through frozen seas. The deep desert offers minerals and silence, and, in some cases, oil beneath the sand. The high mountains offer solitude and timber, and for the communities that have lived on their slopes for generations, a particular kind of beauty that people born at lower altitudes spend their whole lives trying to understand. Even the most extreme places on Earth have made some kind of implicit bargain with the humans who entered them. Here is what I will cost you, and here is what I will give you in exchange. Mars makes no such bargain. Mars offers the scientific riches of an ancient world, yes, and the historical significance of being first, and the long-term possibility of a second home for humanity. But in terms of the immediate daily operational relationship between the planet and the people living on it, Mars offers nothing. It simply presents its conditions. Take them or leave. It has been here for 4.5 billion years and has no opinion about whether you stay. Of all the environmental threats Mars presents, the dust storms are perhaps the most cinematically dramatic and the most operationally disruptive. Mars experiences dust storms on a scale that has no equivalent on Earth. Regional storms, covering areas the size of continents, occur relatively frequently, particularly during the southern hemisphere summer, when Mars is closest to the Sun and temperature gradients in the atmosphere are at their most extreme. These regional storms can merge and escalate. In some years, under the right conditions, they grow into global events that encircle the entire planet, blotting out so much sunlight that the surface dims to near twilight even at midday. The global dust storm of 2018, observed by multiple Mars orbiters and by the Opportunity rover on the surface, lasted for roughly 3 months and reduced surface light levels to less than 1% of normal. Opportunity, which relied on solar panels for power, fell silent and never woke up. A human crew dependent on solar energy during such a storm would face an energy crisis that no amount of careful planning can entirely eliminate. The dust itself is a separate problem from the storms that carry it. Martian dust particles are extraordinarily fine, far finer than household dust or even the finest desert sand on Earth. They're so small that they remain suspended in the thin atmosphere for months after a storm subsides, slowly settling but never fully clearing before the next disturbance stirs them up again. This dust coats solar panels, reducing their efficiency even in the absence of a major storm. It coats the visors of pressure suits, degrading visibility during surface operations. It finds its way into mechanical joints and seals and filters in ways that accelerate wear and create failure points that are difficult to predict and difficult to repair with the limited resources available on the surface. And it carries, as we discussed in an earlier chapter, the perchlorate compounds that make Martian soil toxic to human biology. The dust is not simply an inconvenience, it is a persistent, pervasive, chemically hostile medium that the crew must manage every single day, knowing that a sufficiently large failure in their dust management systems could escalate from an operational problem into a survival problem with very little warning. Solar power is the most practical energy source for early Mars missions, given the prohibitive weight of alternatives, but the relationship between solar panels and the Martian environment is a study in accumulated attrition. Dust deposition reduces panel efficiency by measurable amounts with each passing week. Temperature cycling, the extreme swings between the warmth of a Martian afternoon and the brutal cold of a Martian night, stresses the materials of the panels themselves, creating microscopic cracks that propagate over time. UV radiation, which reaches the Martian surface at higher intensities than it reaches Earth's surface due to the thin atmosphere, degrades the polymer components of solar technology. Each of these effects is manageable in isolation. Together, across months and years of continuous exposure, they represent a slow erosion of the energy foundation on which the entire colony's life support depends. Power is not one concern among many on Mars. It is the concern that underlies all others. Without power, the habitat loses heat, and the Martian night kills everyone inside it within hours. Equipment failure in general deserves a kind of attention that mission plans tend to address methodically, but that popular imagination tends to underestimate. Every piece of equipment a Mars crew depends on was built on Earth, tested on Earth, launched from Earth, and subjected to 6 to 9 months of vibration and thermal stress during the transit to Mars before it was ever used in the Martian environment. The tools and systems that function reliably in Earth laboratories, and even in the controlled environment of the International Space Station, have never been tested at scale in the specific combination of cold, dust, radiation, and perchlorate exposure that Mars presents continuously. Some things will fail sooner than expected. Some will fail in ways that were not anticipated. On Earth, a critical equipment failure can be addressed by ordering a replacement part, flying in a technician, or in an emergency, evacuating the people at risk. On Mars, the nearest hardware store is 140 million miles away, and a replacement part takes at minimum 6 months to arrive, assuming one was already manufactured and ready to launch when the failure occurred. The crew is not simply operating in a hostile environment. They are operating in a hostile environment with no external supply chain and no rescue service within any practical time frame. There is a concept in systems engineering called single point of failure, which describes any component whose failure alone would cause an entire system to collapse. Good engineering tries to eliminate single points of failure through redundancy, building backup systems and alternate pathways so that no single component breakdown can bring down the whole. A Mars habitat will be designed with extraordinary levels of redundancy, because the engineers who design it will understand with absolute clarity what the consequences of an unmitigated single point of failure are in that environment. But redundancy has limits. It adds weight, which is always at a premium in a spacecraft. It adds complexity, which creates its own failure modes, and no amount of redundancy can fully protect against the kind of cascading failure where one problem creates stress on a backup system that was already degraded by dust or temperature cycling or radiation, causing a second failure that overloads the tertiary backup at the worst possible moment. These cascades are rare but not theoretical. They are the scenarios that mission planners spend the most time on and sleep the least over. And then, beneath all the engineering challenges, there is simply the psychological weight of living inside a hostile environment with no margin for complacency. On Earth, even in dangerous professions, there is a background assumption of basic environmental support. The air will continue to be breathable. The temperature will remain within survivable range without active intervention. If you step outside without your equipment, you will be uncomfortable perhaps, but you will not die within minutes. On Mars, the moment a crew member steps outside the habitat without a fully functioning pressure suit, they have approximately 1 to 2 minutes before loss of consciousness and a very short additional interval before death. This is not a metaphor. It is not a theoretical risk. It is the simple physics of an atmosphere that cannot support human life under any circumstances. Living every day with that knowledge, with that particular species of proximity to instant catastrophe, creates a psychological texture to Martian life that has no analogue in any human experience on Earth. You are always, always one equipment failure or one moment of inattention away from the planet asserting its total indifference to your presence. Mars does not hate the people who come to live on it. It simply does not notice them, and that is, in its own quiet way, the most terrifying thing of all. There is a question that sits at the centre of every serious long-term Mars colonization plan. A question that mission architects and bioethicists and reproductive biologists all circle around with varying degrees of directness, and that the public conversation about Mars exploration tends to either skip over entirely or treat as a distant and theoretical concern. It is not distant. It is not theoretical. It is, in fact, the most fundamental question the entire enterprise eventually arrives at, because without an answer to it there is no colony, there are only visitors. The question is this: can human beings successfully reproduce on Mars, and what happens to the children who are born there? Everything we have discussed so far, the physical deterioration, the radiation, the psychological isolation, the unforgiving hostility of the Martian environment, all of it applies to adults who arrive from Earth with fully formed bodies and decades of life experience in Earth gravity. The question of children asks something different and in some ways something far more disturbing. What happens to a human being who never experiences Earth at all? We should begin with what we know, because what we know is already enough to give serious pause. Reproductive biology is exquisitely sensitive to environmental conditions. Radiation, the same constant radiation we explored in an earlier chapter, is particularly damaging to reproductive cells. Both sperm and eggs are vulnerable to radiation-induced DNA damage, and the mutations that accumulate in reproductive cells are not simply personal health risks. They are potential heritable changes, alterations in the genetic code that could be passed on to offspring. The radiation environment of Mars would expose the reproductive systems of everyone living there to doses significantly higher than anything humans have historically encountered in their natural environment on Earth. What this means for the viability of naturally conceived pregnancies for the rate of genetic mutations in the next generation, for the long-term genetic health of a small founding population, is something researchers can model but cannot yet confirm with observed data, because no human being has ever attempted to conceive a child in a radiation environment remotely comparable to what Mars presents. The effects of reduced gravity on reproduction are even less understood because the research simply has not been done. No mammal has ever been conceived, gestated, or born in a significantly reduced gravity environment. We have some data from experiments with simpler organisms and from studies of animal reproduction in microgravity on the International Space Station, but the results are fragmentary and the translation to human reproductive biology is uncertain. What we can reason from first principles is concerning. Fetal development is an extraordinarily gravity-dependent process. The developing embryo and fetus are not simply growing in size. They are organizing themselves in three-dimensional space, differentiating into specific tissue types, migrating cells to their correct positions, building structures whose geometry and orientation are shaped by mechanical forces that include gravity. The cardiovascular system of a developing fetus learns, in utero, to pump blood against the gravitational load it will experience after birth. The skeletal system develops density calibrated to the gravitational environment it is being built for. The vestibular system, the inner ear structures that give us our sense of balance and spatial orientation, develops in response to gravitational cues. What happens to all of these processes in an environment where gravity is 38% of what they expect is, at this point, genuinely unknown? An unknown, in this context, is another word for terrifying. Assume, for the sake of following the logic forward, that conception and gestation on Mars are possible, that the challenges can be navigated with medical support and careful monitoring, and that children are born on Mars. These children will be born into a habitat, into a small pressurized space with recycled air and artificial lighting and the constant background hum of life support systems. They will grow up in 38% gravity. They will never feel Earth's pull beneath their feet. Their bones will develop under Martian conditions, growing longer and thinner than Earth-human bones, optimized for a gravitational load that is less than half of what shaped the skeleton of every human ancestor going back 4 billion years of evolution. Their cardiovascular systems will develop for Martian gravity. Their muscles will grow for Martian loads. By the time they are adolescents, their bodies will be so thoroughly adapted to Mars that placing them in Earth's gravity would not simply be uncomfortable. It could be genuinely dangerous, even lethal, depending on how far the divergence had progressed. This is the moment where the word disappear takes on its deepest meaning in our story tonight. These children will be human in every sense that matters emotionally and socially and culturally. They will have parents who love them. They will have languages and stories and questions and laughter. They will look at the rust-coloured sky through the habitat windows and feel, in whatever way children feel such things, that this is their world, the only world they have ever known. But they will also be, from the moment of their birth, something that has never existed before, not Earth humans, not the fictional aliens of science fiction, something in between and entirely new, human in origin, Martian in body, shaped by a world their ancestors came from but that they themselves can never go to. They will be the first true Martians, and they will carry in their longer bones and lighter frames and radiation-adapted cells the biological signature of a new chapter in the history of our species. The ethical dimensions of this are not small, and they deserve to be named clearly rather than allowed to sit quietly in the background of the technical discussion. Bringing a child into existence on Mars is not simply a personal reproductive decision in the way it is on Earth. It is a decision to bring a being into existence in conditions of extreme hardship, with significant unknowns about their health and development, in an environment from which they may never be able to leave, without their consent and before they have any capacity to understand what they are being born into. Every generation of humans ever born has faced hardship and uncertainty of various kinds. Parents throughout history have brought children into war zones, famines, and catastrophic social upheavals without anything resembling informed consent from the child. But the situation on Mars differs in at least one critical way. The child born on Mars is not simply born into difficult circumstances. They are born into a body specifically shaped by those circumstances, a body that may be permanently incompatible with the world most of their species inhabits. The decision to have children on Mars is, in a very real biological sense, a decision to create a new kind of human being. It is arguably the most consequential reproductive decision in the history of our species, and it will be made, the first time it is made, by a small group of people in a habitat on a distant desert world with imperfect information and the weight of history pressing down on every choice. And yet, from another perspective, it is also the most natural thing imaginable. Humans have children. That is what we do. We have done it in deserts and on islands and in mountain valleys and on the frozen margins of continents where survival required everything the community had. We have always, everywhere, found ways to bring the next generation into existence and to love them and to teach them the world as we understand it. The parents who have children on Mars will not be performing a biological experiment or making a philosophical statement. They will be doing what parents have always done, choosing in the face of uncertainty and risk to continue, to reach forward into a future they cannot fully see and place a life there, and then spend the rest of their own lives doing whatever it takes to protect it. That the life they place there will grow into something different from them, something shaped by Mars rather than by Earth, is not a betrayal of that impulse. It is perhaps its most extraordinary expression. There is a word in evolutionary biology that carries more weight than its two syllables suggest. The word is speciation. It describes the process by which one population of organisms, separated from another population of the same species by geography or environment or time, gradually accumulates enough genetic and physiological differences that the two populations can no longer interbreed successfully. It is the engine that has driven all of the biological diversity on Earth, from the first single-celled organisms in the ancient oceans to the estimated 8 million species alive on the planet today. Every branch on the tree of life represents a speciation event, a moment when one lineage became two, when a single kind of living thing became, across generations and millennia, something new. We tend to think of speciation as a process that happens to other organisms, to finches on isolated islands and fish in separated lake systems and bacteria in different chemical environments. We do not tend to think of it as something that could happen to us. But the people who study human evolution and the people who study the biology of spaceflight are arriving from different directions at the same uncomfortable territory. Mars may be the island, and we may be the finches. The divergence would not begin with genetics, at least not at first. It would begin with the body, in the ways we have already explored across the previous chapters. Bones growing longer and thinner in reduced gravity, muscles calibrating to lighter loads, cardiovascular systems developing for Martian conditions, eyes shaped by different light and different pressures. These are phenotypic changes, changes in the physical expression of the body, and they begin within a single lifetime. The first generation of Mars-born humans would be physically different from their Earth-born parents in measurable ways, not because their DNA had changed, but because the same DNA expressed itself differently in a different environment. The genome is not a rigid blueprint. It is a set of instructions that interacts with its environment, switching certain genes on and suppressing others in response to the conditions it encounters. Put human DNA in Martian conditions and it will build a somewhat different body than it would build on Earth, using the same basic materials arranged according to different environmental signals. But genetics would not stay out of the story for long. Small populations accumulate genetic changes faster than large ones, for reasons that population geneticists have understood for decades. In a small founding population, random genetic drift, the chance fluctuation in which gene variants get passed to the next generation, operates much more powerfully than in a large population where statistical averaging smooths out the randomness. If the founding Mars population is, say, a few hundred people, and if that population is reproductively isolated from Earth, meaning that there is little or no gene flow between the two populations, then genetic differences will begin to accumulate between Martians and Earthlings at a rate that would be essentially invisible in any single generation, but that would become significant across dozens of generations. Some of those differences will be neutral, random variants that neither help nor harm. But some will be subject to natural selection, to the differential survival and reproduction of individuals whose genetic variants happen to suit them better to the Martian environment. Over time, those variants will spread through the population. Over enough time, they will define it. What would natural selection on Mars actually select for? This is where the conversation becomes both scientifically fascinating and ethically complex. Radiation resistance would be a powerful selective pressure. Individuals whose DNA repair mechanisms are slightly more efficient, whose cells handle radiation-induced damage slightly better, would have marginally better health outcomes and slightly higher reproductive success over a lifetime on Mars. Those variants would spread. Efficiency in low-gravity movement and low-gravity cardiovascular function would matter. Body size and bone architecture suited to Martian gravity would be advantageous. Psychological resilience in conditions of isolation and confinement might have heritable components that selection could act on. Over generations, the Martian population would not simply look different from Earth humans. It would be, in a precise biological sense, becoming differently adapted. The process is slow by human timescales. But human timescales are not the only timescales that matter when you are talking about the founding of a new branch of a species. And then there is the deliberate dimension, the possibility that humans on Mars would not simply wait for natural selection to do its work across centuries, but would choose to accelerate and direct the process through genetic technology. This is not science fiction. The tools for editing the human genome already exist. The ethical frameworks for deploying those tools in human reproduction are actively being debated right now, here on Earth, in the context of eliminating heritable diseases. On Mars, the argument for using genetic technology would be more urgent and more immediate than anywhere on Earth. If you could edit the genome of embryos to reduce their susceptibility to radiation damage, to optimize their cardiovascular systems for Martian gravity, to give them better DNA repair mechanisms, the medical case for doing so would be overwhelming. The children who benefited from those edits would be healthier, they would live longer, they would suffer less. The counter-arguments from Earth, the ethical concerns about genetic modification of human embryos, would arrive 40 minutes after they were sent and would be evaluated by people living in an environment that makes the urgency of adaptation impossible to ignore. Here is the thing most people do not realize when they think about the divergence of Martian humans from Earth humans. The divergence would not feel, from the inside, like becoming alien. It would feel like becoming more yourself. The first generation of Martian-born children would grow up knowing no other body than the one they had, no other gravity than the one they moved through, no other sky than the salmon-pink one above their habitat. They would not experience their longer bones and lighter frames as deformities or adaptations. They would experience them as themselves. Their body would be normal, because it would be the only body they had ever been inside. The comparison to Earth humans would be something they knew about intellectually, the way you know about the physiological differences between populations that evolved on different continents, as an interesting fact about biology rather than as a felt sense of difference. The divergence would be real and measurable and profound, but it would be lived from the inside as simply being human on Mars, which is to say, being human in the only way available to you. And yet the question of whether Martian humans and Earth humans would remain the same species, in the technical biological sense, is one that researchers are genuinely uncertain about across long enough timescales. Reproductive compatibility between two populations is the traditional biological criterion for species membership. If individuals from the two populations can produce viable and fertile offspring together, they are the same species. If they cannot, they have speciated. Given the combination of genetic drift in a small isolated population, the action of natural selection on Mars-specific traits, and the potential application of deliberate genetic modification over generations, the accumulation of differences between the two populations would be real and ongoing. Whether it would ever reach the threshold of reproductive incompatibility is impossible to predict, but it is not impossible to imagine. And the fact that it is not impossible to imagine is itself one of the most remarkable things about the moment in history we are living in right now. We are, for the first time, a species contemplating the deliberate creation of its own successor. There is a thought experiment I want you to try tonight, lying wherever you are, in whatever darkness surrounds you. Imagine that you have spent the last 3 years living on Mars, 3 years of 38% gravity, 3 years of radiation accumulation in your bones and tissue and DNA, 3 years of muscles calibrated to a lighter world, of a cardiovascular system that has quietly and efficiently downsized itself for the demands of Martian life, 3 years of eyes that have adjusted to a different light, of bones that have thinned and lengthened, of a body that has been, cell by cell and fibre by fibre, remade by its environment. Now imagine that a spacecraft arrives to take you home. The journey takes 7 months, and then the capsule lands and the hatch opens, and for the first time in more than 3.5 years, you feel the full weight of Earth pressing down on you. Not 38% gravity, 100%. Every kilogram of your body suddenly weighs more than 2.5 times what it weighed when you woke up this morning on Mars, and your body, which has spent 3 years forgetting how to carry that weight, begins to fail. This is not speculation. It is an extrapolation from data we already have. Astronauts returning from 6 months on the International Space Station, which involves near weightlessness rather than 38% gravity, regularly experience serious difficulty readapting to Earth. They cannot walk without assistance for days or weeks. Their cardiovascular systems, which shrank during the mission, struggle to maintain adequate blood pressure in the upright position. They experience vertigo and disorientation as the vestibular system tries to reconcile its space-adapted calibration with the sensory inputs of a full-gravity environment. Their bones, which lost density during the mission, are fracture vulnerable in ways that can persist for months after return. And all of this follows a 6-month mission in zero gravity. Now extend the mission to 3 years. Now change the environment from zero gravity to 38% gravity, which produces slower but still significant physiological adaptation. Now ask what returning to Earth feels like for that person. The honest answer is that we do not know precisely, because no one has ever done it. But the direction of the data is clear, and the direction is not encouraging. For the first generation of Mars settlers, the ones who travelled from Earth as adults, with fully formed Earth-adapted bodies, the question of return is primarily a medical one. It is demanding and uncertain and potentially dangerous, but it is at least theoretically possible. The body remembers Earth, in the sense that it was built for Earth and spent its formative years there. The memory is not perfect, and the longer the time on Mars, the more degraded that memory becomes, but there is a baseline to return to, a biological template that existed before Mars began its slow rewriting. Medical intervention, intensive physical therapy, careful management of the cardiovascular and skeletal systems during readaptation might make return possible for some people even after years on Mars, though the risks would be real and the process would be long and painful. For others, the degradation might simply proceed too far. The window might close not with a definitive medical verdict, but with a quiet accumulation of evidence that the cost of return has become higher than the body can pay. For Mars-born children, the question of return does not even begin in the same place. There is no Earth-adapted body to return to, because there was never an Earth-adapted body to begin with. A child born on Mars under 38% gravity and raised there through adolescence would have a skeletal system, a cardiovascular system, and a muscular architecture that were built from scratch under Martian conditions. Their bones would be longer and less dense than Earth human bones. Their heart would be calibrated for a lighter gravitational load. Their postural muscles, the deep structural muscles that hold the body upright against gravity, would be sized for Mars, not for Earth. Placing that body in Earth's gravity would not be a matter of readaptation. It would be asking a system that was never designed for a particular load to suddenly bear that load without preparation or prior experience. The physics are unforgiving. A skeleton built for 38% gravity under the full weight of Earth is a skeleton at serious risk of structural failure. A cardiovascular system built for Martian conditions trying to maintain blood pressure in Earth gravity is a system that may simply not be up to the task. Here is what makes this particular aspect of the Mars story so quietly devastating when you sit with it. The first generation of settlers will leave Earth knowing, intellectually, that return may become impossible. They will have read the research and attended the briefings and signed the documents, and accepted the risk with as much clarity as human beings can accept, a risk that has no real precedent. They will have made their choice, or at least something that resembles a choice, with adult knowledge and adult agency. But the children born on Mars will make no such choice. They will simply be born into a body that cannot go to Earth, in the way that you were born into a body that cannot breathe water. It will not feel like a limitation from the inside, not in the daily texture of their lives, any more than your inability to breathe water feels like a limitation to you on an ordinary day. But it will be real, and it will be permanent, and it will mean that for those children, and for every generation that follows them, the word home will refer to a place that is separated from the rest of their species by 140 million miles and by a gravitational incompatibility that no technology currently imaginable can bridge. There is an emotional dimension to this that the medical literature tends not to dwell on, but that I think deserves a moment of quiet attention tonight. The first settlers who reach the point where return becomes impossible, whether that moment comes through a clear medical determination or through the slower accumulation of years that has carried them too far from Earth physiology to make the journey survivable, will face something that has no name in our current vocabulary. It is not grief exactly, though grief is part of it. It is not acceptance, though acceptance will eventually come. It is the moment when a choice that was always described as reversible, always framed as an adventure from which one could theoretically return, reveals itself as permanent. The one-way mirror that opened the very first chapter of our story tonight. They pressed their hand against the glass and stepped through, and the glass closed behind them. Not dramatically, not all at once, but closed nonetheless, in the particular silent way that biological reality closes doors, without announcement and without apology. And yet, and this is the part that I find myself returning to again and again when I think about this, the impossibility of return is not only a loss, it is also a commitment. It is the moment when Mars stops being a destination and becomes a home, not as a metaphor but as a biological fact. The body that cannot return to Earth is a body that belongs to Mars in the deepest possible sense, a body shaped by Mars, sustained by Mars, and now permanently bound to Mars. There is something in that permanence that goes beyond tragedy, something that the great explorers and settlers of human history would recognize. The people who crossed oceans in wooden ships knowing that they would likely never see their homeland again, who built new lives in new places and raised children who knew only those new places and carried the old country only as a story. Mars will be the most extreme version of that human pattern, the farthest anyone has ever sailed, the shore from which there is no sailing back, and the people standing on it, unable to leave and uninterested eventually in leaving, will simply look up at their salmon-coloured sky and call it what it is, theirs. There is a vision of Mars that lives in the long imagination of the people who think most seriously about its future, a vision so vast in its ambition and so patient in its timescale that it makes the entire history of human civilization look like a brief afternoon. It is the vision of a green Mars, a wet Mars, a Mars with a thick blue sky and open rivers, and perhaps, in its warmest equatorial valleys, something that a person from Earth might cautiously call pleasant. This vision has a name, terraforming, from the Latin for earth-shaping. The deliberate, systematic, multi-generational transformation of an entire planet's climate and atmosphere and surface chemistry into something compatible with unprotected human life. It is the most ambitious engineering project ever conceived by our species. It would take not decades, but centuries, possibly millennia, and the people who begin it will never see it finished. They will plant trees, in the most literal and the most metaphorical sense, in whose shade they will never sit. That is, when you think about it carefully, one of the most extraordinary things a human being has ever been asked to do. The first challenge of terraforming Mars is the one that underlies all the others. The planet is too cold, too thin, and too exposed. The average surface temperature of minus 60 degrees Celsius needs to rise by roughly 60 degrees before liquid water can exist stably on the surface. The atmospheric pressure, currently less than 1% of Earth's, needs to increase by a factor of roughly 100 before it provides meaningful radiation shielding, and before the boiling point of water rises high enough to make liquid water viable at surface temperatures. The magnetic field, which would be needed to prevent the newly thickened atmosphere from being stripped away by the solar wind over geological timescales, is gone and cannot be regenerated by any technology currently foreseeable. These are not engineering problems in the conventional sense, the kind that yield to sufficient ingenuity and resources within a human lifespan. They are planetary-scale physical realities that can only be nudged slowly and persistently in a desired direction over timeframes that dwarf the entirety of recorded human history. The most commonly discussed first step in any serious terraforming proposal is warming the planet, and the primary mechanism proposed for doing so involves amplifying the greenhouse effect on Mars in much the same way that industrial emissions are unintentionally amplifying it on Earth. Mars has abundant carbon dioxide frozen into its polar ice caps and locked in its soil. If the planet can be warmed enough to begin releasing this carbon dioxide into the atmosphere, A feedback loop could potentially be initiated in which the thickening atmosphere traps more heat, which warms the planet further, which releases more carbon dioxide, which thickens the atmosphere further, and so on in a self-reinforcing cycle. The question is how to provide the initial warming impulse powerful enough to trigger the cycle. Proposals have included orbiting mirrors that concentrate sunlight onto the poles to sublimate the ice caps, factories on the Martian surface producing powerful synthetic greenhouse gases, and the deliberate redirection of carbon-rich asteroids to impact the planet and deliver both heat and raw material. Each of these approaches faces engineering challenges that are, to put it gently, significant. But each is at least physically plausible, which is more than can be said for some of the later stages of terraforming. Assume the warming works. Assume that over the course of a century or two, the mean surface temperature of Mars rises by the necessary 60 degrees. The polar caps begin to melt. Carbon dioxide floods into the atmosphere. Pressure begins to climb. Ancient ice deposits beneath the Martian surface, which orbital observations suggest may be substantial, begin to melt and flow. Riverbeds that have been dry for 3 billion years carry water again, briefly and then more persistently, carving new channels through the ancient rust. This is the moment that terraforming dreamers hold in their minds like a private sunrise, the moment when Mars begins to look, from a distance, like it might once have looked when it was young and wet and perhaps, 4 billion years ago, alive. It is a genuinely moving vision, and it is also, from the perspective of the people actually living on Mars at that time, still completely uninhabitable without a pressure suit, because carbon dioxide at higher pressure is not breathable oxygen, and a warmer Mars is not a livable Mars, it is simply a less immediately lethal one. The introduction of oxygen into the Martian atmosphere is the step that turns warming into habitability, and it is the step with the longest timeline of all. Oxygen does not appear spontaneously in planetary atmospheres. On Earth, it accumulated over roughly 2 billion years through the metabolic activity of photosynthetic microorganisms, cyanobacteria that consumed carbon dioxide and released oxygen as a byproduct, gradually transforming an atmosphere that was initially hostile to oxygen, breathing life into the air-filling 21% oxygen environment that we breathe today. The same process, deployed on Mars, would take similar timescales, even with deliberate human acceleration through the introduction of engineered photosynthetic organisms optimized for Martian conditions. We are talking about timescales measured in thousands of years, at minimum, tens of thousands of years in more conservative estimates, before the Martian atmosphere could support unprotected human breathing. Every generation of Martian humans between now and that distant moment would live and die inside habitats and pressure suits, working toward a transformation that no individual among them could witness more than the most infinitesimal fraction of. This is the part of the terraforming vision that I find the most genuinely staggering, not the engineering challenges, not the energy requirements, not the geopolitical complexity of coordinating a planetary-scale project across centuries of changing human civilization. It is the human dimension of working across timescales that make individual lives seem almost vanishingly brief. Every engineer who designs a terraforming system, every biologist who develops the photosynthetic organisms that will be seeded across the Martian surface, every administrator who allocates resources to the project, every child born on Mars who grows up understanding that the sky above them is wrong and will one day be right, is participating in a project whose completion they will never see. They are contributing to a future they can only imagine, working in service of people who do not yet exist, on a timescale that makes their own presence in the story almost poignantly small. It is, in the truest sense of the word, an act of faith. Not religious faith, but something structurally similar. The commitment of present effort and sacrifice to a future good that transcends any individual life. And here is the question that sits underneath all the engineering timelines and atmospheric chemistry and population biology, the question that terraforming eventually forces you to confront directly. By the time Mars is habitable without a pressure suit, the Martian humans living there will have been evolving and adapting and diverging from Earth humans for thousands of years. The body that walks out onto an open Martian surface breathing Martian air for the first time will not be the body that the first settlers brought from Earth. It will be something that Mars made, over millennia of selection and drift and deliberate modification, shaped for that very world. The terraformers will not be making Mars habitable for Earth humans. they will be making it habitable for Martians, for beings who, by the time the sky finally turns blue, may have as much in common with the first settlers as we have in common with the first members of our own genus who walked upright across the African savanna more than 2 million years ago. The project of terraforming Mars and the project of transforming the humans who live there are not separate projects running in parallel. They are the same project, proceeding at different speeds, both pointed at the same distant horizon where a new kind of life on a new kind of world finally becomes possible. Think about what you know of your grandparents' world. Not the facts you learned from history books, but the living texture of it, the particular quality of the light in the places they grew up, the sounds of the streets they walked as children, the specific weight of the concerns that shaped their daily lives. Even if you knew them well, even if they told you stories and showed you photographs, there is a distance between your experience of the world and theirs that no amount of storytelling fully bridges. The world they were born into is gone, and your knowledge of it is second-hand, assembled from fragments rather than lived from the inside. Now imagine that distance not as one generation, but as 10 or 50. Now imagine that the separation is not simply temporal but planetary, that the world your ancestors came from is not gone but is still there, still turning, still full of people, just impossibly far away and fundamentally incompatible with the body you now inhabit. That is the relationship that Martian humans, within a handful of generations, will have with Earth. And the thinning of that connection, the slow and irreversible process by which a place becomes a legend, and then a myth, and then something closer to a creation story, is one of the quietest and most profound transformations in our entire story tonight. The first generation of Mars settlers will maintain fierce and tender connections to Earth. They will have left people there, parents, siblings, friends, colleagues, the entire social fabric of a life built on one world that was then deliberately and irreversibly abandoned for another. They will follow Earth news with the intensity of exiles, tracking the politics and the culture and the sports results and the deaths of people they love across a communication delay that makes every exchange feel like a letter rather than a conversation. They will celebrate Earth holidays and cook approximations of Earth food from whatever ingredients the Martian agricultural system can produce, and they will tell their children about rain and oceans and the particular blue of an Earth sky in a way that carries the specific ache of describing something you love to someone who will never see it. Their connection to Earth will be real and deep and actively maintained, because it will be the connection to everything they were before Mars began to make them into something new. The second generation, the children born on Mars to Earth-born parents, will have a different relationship to Earth entirely. They will know it through their parents' stories and through the data streams that arrive from Earth on a 40-minute delay, through the accumulated archive of human culture that the settlers will have brought with them, through whatever educational curriculum the colony develops to ensure that Martian children understand the world their parents came from. But they will know it the way you know a country you have studied extensively but never visited. Intellectually rich, emotionally adjacent, never quite immediate. Earth will be real to them in the way that ancient Rome is real to someone who has spent years reading about it. Vivid in the imagination, genuinely meaningful, but finally and fundamentally elsewhere. They will feel affection for Earth, probably, the way people feel affection for ancestral homelands they have never seen. A warm and somewhat abstract loyalty to a place that shaped everything about their origins without ever having directly shaped them. Language is where the divergence tends to announce itself first in separated human populations, and Mars will be no exception. The settlers will arrive speaking whatever languages they brought from Earth, likely a mixture dominated by whatever nationalities and institutions funded and staffed the mission. English seems probable as a common operational language, alongside whatever other languages the crew members carry as native tongues. But language is not a static artifact. It changes continuously in response to the environment and experience of its speakers, accumulating new words for new things, and losing or transforming words for things that no longer exist in the community's daily life. On Mars, there will be new things that need naming, new geological features, new operational concepts, new social structures and new experiences and new categories of sensation that Earth languages have no words for because Earth humans have never encountered them. And there will be Earth words that drift in meaning, or fall away entirely, because the things they describe are absent from Martian life. What is the Mars word for rain, for forest, for the smell of wet earth after a storm. Either the words persist as historical artifacts, museum pieces of language kept alive by cultural effort, or they fade, as words always fade when the things they describe are no longer part of daily experience. Culture will follow the same trajectory as language, but more slowly and with greater complexity. The settlers will bring with them the full richness of Earth's cultural heritage, its music and literature and visual art and philosophy and religion and science. Thousands of years of human meaning-making compressed into the data storage of a Mars-bound spacecraft. They will not abandon this inheritance. They will teach it to their children, and those children will teach it to theirs. Because culture is how communities transmit identity across time, and the first Martians will understand with particular urgency how important it is to remember where they came from. But culture, like language, is not static. It evolves in response to the lives of the people who carry it. New art will emerge that makes no sense without the context of Mars. New music that incorporates the sounds of the habitat, the rhythm of life support systems, the particular silence of a dust storm pressing against reinforced walls. New literature that takes for granted the salmon sky and the ancient craters and the 40-minute gap between a question and its answer. Within a few generations, Martian culture will be recognizably descended from Earth culture but no longer identical to it, in the same way that the cultures of the Americas are recognizably descended from their European and African and indigenous roots, but constitute something distinct that those roots alone could not have predicted. Religion and philosophy face their own particular Martian transformations. Every major human religious tradition evolved in response to the experience of life on Earth, to its cycles of day and night and season, to its particular relationship between humanity and the natural world, to its specific existential conditions of birth and death, and suffering and love under Earth conditions. A Martian day, called a sol, is 24 hours and 37 minutes long, close enough to an Earth day to be livable, but different enough to create a permanent low-level desynchronization with Earth's calendar. The Martian year is roughly 687 Earth days, nearly twice as long. The seasons are extreme and asymmetric. The relationship to the natural world is one of absolute dependence on artificial systems, rather than the organic embeddedness that underlies most Earth spirituality. How do the great Earth religious traditions translate into this context? Some elements will carry over with remarkable resilience. The human experiences of love and loss and wonder and moral struggle are not gravity-dependent, but others will require translation so deep that they become, in effect, new traditions. And some new traditions will emerge that have no Earth precedent, born from the specific existential conditions of being a small community of human beings on a dead world, working across centuries toward a transformation they will never see completed, sustained by a connection to a home planet that grows thinner with each passing generation. The last direct living connection to Earth will be a person. Somewhere in the future of this story, there will be a Martian who is the last surviving individual who was actually born on Earth, who has actual memories of Earth gravity and Earth sky and Earth rain, who knows in their body rather than their education what it felt like to stand on the original world. When that person dies, something will change in the Martian community that will not be captured in any demographic record. The living memory of Earth will have ended. What remains will be stories and data and cultural artifacts and the genetic record carried in every Martian body, tracing its ancestry back across 140 million miles to a blue planet that the last generation of Martians knows only as their most ancient and most beloved myth. There is a river in Central Africa called the Congo, and somewhere in its ancient basin, several million years ago, a population of our earliest ancestors became separated by a shifting landscape into two groups that would never reconnect. Over hundreds of thousands of years, those two groups diverged. One remained in the forests, one adapted to more open environments. Their bodies changed, their social structures changed, their cognitive capacities developed along different lines in response to different pressures. Today we recognize those two lineages as distinct species. They shared a common ancestor. They were, at the moment of separation, the same creature. And then time and distance and different environments made them into two different kinds of being, each one a complete expression of life, neither one diminished by the existence of the other, both of them the product of the same ancient origin story written in the same ancient river basin. What is coming on Mars is not identical to that story. It is faster, and it is deliberate, and it is happening to a species with the self-awareness to watch it unfold in something approaching real time. But the deep structure is the same: one lineage, two paths, a divergence that, once it begins in earnest, does not reverse. Picture the solar system as it might look several hundred years from now, seen from a sufficient distance that both planets are visible simultaneously, both turning slowly in their orbits around the same sun. On one, a blue world with white clouds and brown and green continents and 7 oceans and 8 billion or 12 billion or whatever number of human beings the planet is carrying by then, going about the incomprehensible complexity of human civilization with all its beauty and cruelty and creativity and conflict. On the other, a rust-red world with expanding patches of green in its equatorial regions and a slightly thicker sky and pressurized habitats clustered around the ancient volcanoes and canyon systems, home to a population of beings who are recognizably descended from the first, but who are no longer, in a precise biological sense, identical to it. Two expressions of a single origin, two humanities unfolding in parallel, shaped by different suns, different gravities, different challenges, different timescales of adaptation. The space between them, 140 million miles of vacuum and starlight, is simultaneously nothing, a trivial distance on the scale of the galaxy, and everything, an unbridgeable biological and experiential gulf that no spacecraft can fully cross. The relationship between these two humanities will be one of the most complex and consequential relationships in the history of either of them. It will not be simple or static. In its earliest phase, it will look like the relationship between a parent civilization and a colony, with Earth providing resources and expertise and cultural transmission, and Mars providing scientific returns and the psychological reassurance that our species has successfully taken its first step beyond the cradle. But colonial relationships do not stay simple, and the history of Earth offers no shortage of examples of what happens when a distant community, shaped by its own environment into something distinct from the civilization that founded it, begins to develop interests and identities that diverge from those of the founding culture. The American colonies, the settlements of Australia, the frontier communities of every expanding civilization in human history. Distance creates autonomy. Autonomy creates identity. Identity eventually demands recognition. And the Martians, whose bodies will be so thoroughly shaped by their world that return to Earth may be biologically impossible, will have a claim to autonomy that is more absolute than any previous colonial population in human history, because it will be written not just in their politics, but in their bones. There will be tensions. This seems as close to certain as anything in this story. Economic tensions over the cost of maintaining supply lines across interplanetary distances. Political tensions over who has authority over decisions that affect the Martian colony. Cultural tensions between a Mars community that is evolving its own identity and an Earth civilization that may struggle to recognize in its Martian descendants the humanity it projected onto them. And there will be a deeper tension, harder to name and harder to resolve, that arises from the simple fact of biological divergence. When two populations of the same species become sufficiently different from each other, the category of sameness that previously connected them begins to feel uncertain. Earth humans and Martian humans will share an origin, a genetic ancestry, a cultural heritage, a common history going back to the same first cells in the same ancient oceans, but they will inhabit bodies that have been shaped by different worlds for different purposes, and they will live lives that are as different from each other in their daily texture and physical reality as the lives of any two populations on Earth have ever been. And yet here is what I want you to hold alongside that picture of divergence and tension. The two humanities will also share something that no amount of biological divergence can erase. They will share curiosity. They will share the capacity for love and grief and wonder and the telling of stories. They will share the impulse to look up at the night sky, from whichever world they stand on, and feel the particular vertigo of smallness that comes from confronting the scale of the universe. Earth humans looking up at the night sky will see Mars as a reddish point of light and know that their distant relatives are there, living improbable lives on an improbable world. Martian humans looking up through their thickening atmosphere will see Earth as a blue star and feel, in whatever way the children of exiles feel such things, the pull of an origin they carry inside them without ever having experienced it directly. That pull, that thread of connection across the void, is not nothing. It may be the most important thing. It is the proof that whatever divergence produces in terms of bodies and cultures and political systems and perhaps eventually species boundaries, the origin was shared, the curiosity was shared, the leap into the unknown was shared, and that sharing matters in a way that is difficult to quantify and impossible to dismiss. The cosmic irony at the heart of this entire story, the one that has been quietly present since the very first chapter, is this. The strategy most likely to ensure the long-term survival of humanity is also the strategy most likely to end humanity as a single unified thing. A species that lives on only one world is a species whose entire existence depends on the continued habitability of that one world. A catastrophic asteroid impact, a runaway climate shift, a pandemic, a nuclear exchange. Any number of scenarios could theoretically end a single planet civilization without remainder. A species distributed across two worlds, with two separate populations adapted to two separate environments, is far more resilient. The extinction of one branch does not mean the extinction of the species, but the distribution that protects the species also inevitably divides it. The same separation that makes each branch safer makes the two branches different. You cannot have the insurance without the divergence. You cannot spread without separating. You cannot survive as a species without, in some meaningful sense, ceasing to be a single species. This is not a paradox that can be resolved. It can only be accepted, with whatever mixture of sadness and wonder and pride you can bring to the acceptance of something both inevitable and extraordinary. Two rivers, flowing from the same source, diverging across a landscape neither of them chose, each one carrying the water of the origin forward into a future the source could never have predicted. That is what is coming. That is what we are right now, in this peculiar and remarkable and terrifying and beautiful moment of history, in the earliest possible stages of setting in motion. The first humans on Mars will not know, when they step off the lander into the rust-coloured silence, that they are the moment of divergence. They will think they are explorers, which they are. They will think they are pioneers, which they are. They will not be thinking in that moment of arrival about speciation and genetic drift and the slow biological transformation of their descendants across thousands of years. They will be thinking about the view and about the work ahead and about the people they left behind. But the divergence will begin anyway, as it always does, not with a decision, but with a step. We have travelled a long way tonight. We began in the cold silence of a world 140 million miles away, pressing a hand against a one-way mirror, and we have followed the story of our species across timescales that make individual lives feel like single notes in a symphony that stretches beyond the horizon of anything any one person will ever hear in its entirety. We have watched the human body begin to forget Earth from the very first day of arrival. We have sat with the invisible radiation falling through a sky that offers no protection. We have looked into the eyes of people in a small habitat, surrounded by the most hostile environment any human being has ever chosen to inhabit, and tried to understand what it costs them and what it makes of them. We have imagined children born under a salmon sky who will never feel Earth's gravity and will never need to. We have traced the slow, patient, unstoppable process of divergence that will, across centuries, make the descendants of those first settlers into something the universe has never contained before. And now we have arrived at the place where all of these threads come together, not in a resolution, because this story has no resolution yet, but in a resting place, a moment of stillness before sleep. Here is what I want you to take with you into the quiet of tonight. The first humans on Mars will slowly disappear. This is true. It is scientifically grounded and philosophically serious, and it carries a weight that deserves to be felt rather than argued away. Their bones will change. Their eyes will change. Their minds will be shaped by an isolation and a silence, and a set of existential conditions that no human being has ever navigated before. Their children will be born into bodies that Mars is already making for itself, bodies that grow longer and lighter and differently calibrated than the bodies that left Earth. Their grandchildren will look at Earth in the night sky the way you look at a star, with awe and affection, and the particular tenderness we feel for things that are beautiful and unreachable. And their descendants, across generations too numerous to count tonight, will become something that sits at the edge of what our current language can hold. Human in origin, Martian in form, belonging to a lineage that began in the same ancient oceans as everything that has ever lived on Earth, and that has now, for the first time in 4 billion years of life on this planet, carried that lineage somewhere else. But here is the other thing I want you to hold alongside that. The thing that I think matters just as much, and that gets lost sometimes in the clinical precision of the science. The disappearance is also an appearance. Every transformation involves a loss and a becoming, and the becoming is as real as the loss. The Earth human who steps onto Mars and begins to change is not simply diminishing. They are also, in a way that is difficult to fully articulate but impossible to dismiss, expanding. Expanding the range of environments in which human life is possible. Expanding the definition of what a human body can be and what a human life can look like. Expanding the territory of the living in a universe where the living are, as far as we currently know, vanishingly rare and extraordinarily precious. The first Martians will disappear as Earthlings and appear as something new, and that new thing will carry forward into an unimaginable future. The same essential curiosity and courage and capacity for wonder that sent the first of them across 140 million miles of empty space in the first place. That is not a loss. That is the oldest story our species knows, told at a scale we have never attempted before. We are the universe noticing itself. This is not a poetic sentiment. It is, as best as science can determine, a literal description of what is happening when a conscious being looks up at the night sky and feels the scale of it and asks what it means. The universe is approximately 13.8 billion years old. For the vast majority of that time, as far as we know, nothing in it was aware of its own existence. Matter formed and collapsed and exploded and reformed for billions of years before the particular chain of events that produced life on Earth, and billions more years passed before life on Earth produced something capable of turning its attention outward and asking what it was looking at. We are, each of us, a brief and improbable arrangement of atoms that has somehow achieved the capacity to be astonished by the other arrangements of atoms surrounding it. That astonishment is what drove the first skywatchers to track the movement of the red wandering light. It is what drove Lowell to his telescope. It is what drove Carl Sagan to describe Mars as a world that beckons. And it is what will drive the first humans to accept the terms of a one-way mirror and step through it into a world that will slowly and completely remake them. The universe, in all of this, is simply continuing to notice itself through new eyes. And now, for the first time, those eyes will be looking back at Earth from somewhere else. There is something that the stars have been doing for the entire duration of tonight, while we've been talking. They have been moving. Not dramatically, not in any way your eye could detect across a single night, but the stars are moving, all of them, relative to each other and to us, following the slow gravitational choreography of the galaxy. The light you see when you look up at the night sky left its source years or decades or centuries or millennia before it reached your eye. Some of the stars you can see tonight no longer exist. They burned out before the light you are receiving from them even completed its journey. You are looking at a sky that is partly history, partly present, and partly an arrangement that will never quite repeat. The stars do not know you are watching, but you are watching anyway, because that is what it means to be the kind of creature we are. Creatures who look up, creatures who ask, creatures who, apparently and against all reasonable odds, find ways to go. The first humans on Mars will carry that looking upward with them. They will stand on the surface of another world, sealed inside their suits, and they will look up at a sky in which Earth is a bright blue star, and they will feel something that no human vocabulary quite has a word for yet. Not homesickness exactly, though that will be part of it. Not wonder, though that will be part of it too. Something that encompasses both and transcends both. A feeling that arises only when you are standing somewhere you were never supposed to be able to stand, looking back at everything that made you, knowing that you cannot return to it, and finding in that knowledge not only grief, but something that might be called a terrible and magnificent freedom. They will stand there in the rust-coloured silence under the radiation-drenched sky, on the toxic ancient soil farther from home than any human being has ever stood. And they will be, in that moment, the furthest forward edge of 4 billion years of life reaching outward into the dark, the universe, through their changed and changing eyes, noticing a little more of itself. Thank you for joining me tonight on this long, quiet journey across space and time in the strange and beautiful territory of what it means to be human in a universe this vast. If this kind of exploration moves something in you, if these questions about where we came from, and where we might be going, keep you company in the dark the way they keep me company, please take a moment to like this and subscribe to the channel. It is a small thing, but it is how more curious minds like yours find their way to these conversations, and that matters more than I can say. Tonight, before you drift into sleep, I want to leave you with one last thought. Step outside tomorrow night, if you can. Look up, find the reddish point of light, if Mars is visible from where you are, and hold it in your attention for just a moment. Somewhere in the future, someone is going to stand on that point of light and look back at you. They will be different from you. They will be shaped by a world you will never visit, but they will come from the same place you come from, the same star, the same story, the same reaching outward into the dark that is the oldest and most human thing there is. Sleep well tonight. Keep looking up at the stars. Good night.